What's up, what's up, what's up, what's up? Welcome back. Today we're working on my image to ASCII, image to UTF-8 neural network. So the idea is we have images here on the left and we convert them into like a text representation on the right. Right, if you look at like what's actually in here, these are a lot of characters that come from like a specific font rendered out as rectangular glyphs and then shoved back into a picture, completely black and white. And the thought process here is there is some form of rule set that we can generate or that we come up with that basically converts a sample for like what a single block, like what a single glyph occupies. We can find some metric that's like, what is the best glyph for this spot? And that's different than like just pure brightness, right? We actually have the pure brightness version here. If we look at that, that's like a way worse representation of the image than what we've actually ended up with, right? And so the thought is that using some sort of heuristics, we can come up with a way to basically match glyphs at like a sub-glyph level. So here we can see like, here are like the best parts for, let's try to find like a boundary here. Give it a sec to load. So here, right, we have like dark at the top, white at the bottom. We have like some sort of character that has white at the bottom, dark at the top. And that is better, right? Now, what we found was that we came up with this like this heuristic, which is basically like render the glyph as an image, render every single glyph as an image, take this sample that we're trying to look at and compare it to every single glyph, pixel by pixel. Maybe we like blur the glyph a little bit so that it has some sort of area effect, and basically find like the thing that has like the lowest distance from that, and then we like weight it by brightness a little bit as well so that we get like an approximate correct looking thing to us as a person. And that worked like pretty well, except it runs like pretty slow, like maybe like a couple seconds for a 1080p image. And when we basically feed this into like a neural network training algorithm, and we try to basically compress that information down into a neural network. So we have like like a pretty shitty neural net. We have basically like, I think it's one input for every single pixel. So this will be like however big the sample is. So it's like 6 by 9. We're gonna have what's 6 times 9, 54 inputs. And then we have like 4,000 outputs, one per each UTF-8 character. I don't know if it's actually 4,000, but it's a lot. It's a lot more than like your typical ASCII range. And then in the middle, we just have like one hidden layer of like 15 nodes. And so the idea is that like each one of these nodes gets multiplied by each pixel, and then each one of these outputs gets multiplied by each node. And so we have like some computation on the order of like number of characters plus number of pixels times 15. It's like approximately how much, maybe times 2 times 15, like is approximately how many like floating point operators you have to do. And that gets us down to like 10 milliseconds for a 1080p image on the CPU versus like the 2 seconds that it took to run the metric by hand. So it's working pretty good. And the thought now is we need to do something with this, right? Like say we want to build this into some application. Maybe we like want to run the filter on the webcam, or we want to like put it on the internet so that people can like textify images, whatever. We need to like start using a non-toy programming language to do that. So Python we've been using because it's like where PyTorch lives, and people like using it for like fast scripting and stuff, but it doesn't really feel like what I want to use for like a real application. And so today I wanted to explore how would we like take this graph and basically like import it into a real programming language. And there are like ways to do this that I think that like people in the real world use. So you can like export the weights from PyTorch as like, you can either like trace all of the things that you're doing. So like as you run your code, you can just like, PyTorch will like write down, he's like, okay, he did this, then he did this, then he did this. And he like saves that as like a computational graph that can be re-imported from C++. But then you have to use PyTorch's C++ library. And then there's like this like open format that I was reading about. I think it's called Onyx, ONNX. And it's like a representation of your computational graph that is like standardized, that you could like train something in PyTorch and run it with some other backend. And we can use that, except then I have to use all phonics. And, you know, we have is like the world's like simplest neural network, right? We don't have any of like the fancy shit. We just have like essentially like what are multiplies and adds. And then I think we have like some like ReLUs in there. So just like one like cut, like a basically a min max as well. And so we should be able to figure out how to do that ourselves. And if we figure out how to do it ourselves, it proves that we have like an understanding of what's going on under the hood, which is like very nice for us to have. Also, we have we have not invented here syndrome, so we just have to do everything ourselves. It's more fun, and we're here for fun, right? Like so, that's what we're doing. And so I think like the plan of action is we have like some code that we run with some weights loaded by PyTorch, and we have to figure out some way to like export those in a way that's like importable from another language. Then we can probably try like re-importing that back into PyTorch and just rerunning it, make sure we get like the same thing, or that like our model looks approximately the same after. And then once we do that, then we can figure out how to like load it in Rust and actually execute the graph in Rust or whatever. That's the plan. That's the plan. So I think the first thing to do is like look at what the fuck is our neural network doing, and can we figure out how to represent that in some way. So hello, network. Here we go. So I think this is where we're looking. And it's a very, very simple network, right? We have what we drew up in Paint, essentially. So 2 linear layers, and when we execute, we run the linear layer 1, we run a rectify linear on all of the outputs, and then run linear 2. So if I understand this correctly, this should look like, let's see, we have an input to our neural network that is num inputs times num outputs long. So we're going to take in like 2D sample, and we're going to turn that into just a flat array of floats. So to num inputs floats. Then we are going to, we have 15 nodes in the middle. And each of those 15 nodes is multiplying by each of the inputs. So we should have like 15 times number of input multiplies here, and then 15 adds, I think. We can probably do something like make a little test script. And in our test script, maybe we just load the network and start poking it a little bit. So, hey, Abil, thanks for the sub. Appreciate it. Okay, so let's just clear this whole thing. ChatGPT 5, we're so far from that, dude. Those things are crazy. Like, we've come a long way. Yeah, ChatGPT 0.00005. That sounds more reasonable. Yeah, those things are nuts. We've come a long way from like, basically what we have here is like what people were doing like 10 years ago, right? Just like simple linear neural networks. Like you watch like videos of like, I trained a neural network to play Mario. And like, this is essentially what they were doing back then. And those like, ChatGPT is like so far from that. Like they've come up with a lot of like intermediate representations and stuff that, yeah, that allow a lot more complexity. It's crazy. Okay. What are we looking for? We are trying to load the parameters. So something like this. How old are you? Oh, I'm like 30. You know, we're old around here. I guess not old in the world of like professional programming, but old in the world of people who are on Twitch. So we can say here, if name equals main. Oh, you were guessing 23 or 24. I'm 37. I guess that's flattering. I'll take it. 30. So, okay, what's it like as a 37-year-old Twitch viewer? There's got to be like only children in your eyes on this platform, right? Like I feel like I'm pretty old for Twitch, and I'm a lot closer. Okay, main. And what are we looking at here? We want to load the parameters, which means we need weights and parameters. So we can just hard code those for now. So we'll say network params path is. I think we have these guys here. Oopsies. Here, this is what I'm looking for. So we have weights and params here. I don't think there's any difference between 25 and 37, to be honest. Yeah, you know what? I'll take that. But that's kind of what I feel like talking to older people as well. Like, there's like, you've graduated, you're like fresh grad. That's kind of like its own thing. And then there's like, you're in the working world. And then it seems like till you have kids, there's like no difference in like life. It's like what, at least that's what I've observed. But I guess maybe some people mature more. So network params path is equal to this. And the network weights is equal to this. And then we should be able to load this guy. We need device, so we'll say device is equal to CPU for now. And then we need to pull in those imports. So this. And why is he unhappy still? I'm pretty sure this is fine. And then here, we can then start poking the network. So what were we even trying to do? We were trying to look at what is inside the first linear layer. So linear 1. Let's just like print out what this is. Okay, so we have in features, out features. Okay, sure, but like what is it, you know? We have this like weight field, and there we go. This is kind of what I was looking for. And so what is he? He is a bunch of floats that are multipliers, and he is input. He's got shape of 15 by 54. So 54 is probably the size of the input. Sample width and sample height are probably 6 and 9 in that case. Let's look at the network params and just see what those look like. So we have sample width 6, sample height 9. So yeah, so we have, for each of the 15 nodes in the middle, we have a multiplier for each of the inputs. Okay, cool. And then probably, I think we have like an adder as well. I think they call it bias. Yeah, so they have 15 additions. So it looks like they have multiplier here, add here, multiplies here. So then if we look at the second linear node, we should see, what do we expect to see here? We expect to see number of characters output times the 15. And we see 1500 characters output, 1525, 15. Okay. And so I guess this array format is for each output character, what are my weights for each of the inputs? Okay, makes sense, sure. Seems fine. And then probably here we have a bias as well. Yeah, okay, that's easy. Easy. Okay, so what I'm thinking is, we can store this as some sort of computational graph, right? So each you can imagine like one pixel getting fed in here, and he's like one of the many inputs to this node here, and we have edges on our graph that are multipliers, and then we can also maybe represent the adds as like other edges. So we could have, basically we could consider like nodes on our graph as a data at a point in the computation, and you could then say that to get to the output, you need to look at like a previous input, and you have to know, you could then be like, well, I don't know what that input is yet. I haven't calculated yet. And so then you could like move backwards from there to figure out what the like mathematical operation that you need to do to get there is. I think that makes sense. So you could, if we like strip this down into like, say we have like two inputs, two nodes in the hidden layer, and two outputs. This, I guess, we would like say this is the multiply that comes out, then this is the add that we need to get to here. Then we store like another multiply here, add to get to here, and then we have this number, which is our output. So we can like break up each of these things. And then what we can do is like, once we have like this graph, which is going to be like, you know, heavily multiplied out, but there's going to be like a lot of things. We could store each node, store each edge. And that should be enough to like reconstruct the computation. I'm not really sure, but it seems reasonable to me in my head. So let's say that we had like operations, right? We could have like a like multiply operation and a add operation. And then we also have a rectified linear operation, we can call it. Maybe. I'm trying to, sorry, my brain's spinning because I'm trying to see if like this translates back into PyTorch at all. But I guess we'll find out. So, in our case, our network is a network. And I guess we kind of have to encode the order of operations in here. But maybe what we first do is let's just first encode one layer, this one linear layer, and we can kind of see how that plays out, see how it feels, and once we have that, then we can start tacking on operations. So that first linear operation is just multiplies and adds. Okay. So let's say that we have like, I guess we are going to have to store okay, so this idea of like storing each intermediate piece of info as a node, that means that we are actually storing inputs to each node, I guess, as weights. So the weights are like, here, to get to here from here, I need to multiply by some number. That's essentially it. I'm just multiplying by some number. And here I am multiplying. Oh, it's multiplying by some number and multiplying this input by another number. Okay, so like for each node in the graph, we could think of, he has like some attributes with him. How do I want to write this out? For now, let's just write it out as like a Python thing. So he has like an operation that he's doing, which is like multiply. And I guess he has like inputs, which are like nodes, other nodes in the graph, I guess. So this would be like node IDs, I guess. So we would have something like nodes, which is like an array of things. An array of things that look like this. Yes. And for each node, he might have an input that is another node in the graph. Might have an input that's another node in the graph, or something that we like inject at the start, right? So like when we're like at the very first point here, we have some input that is like fed in by us, the user of the network. What are you doing? Yeah, I'm not really like describing it very well. I'm trying to store a neural network as like an arbitrary graph so that I can import it by hand in another language and run it myself. And I'm trying to like decide on a data format for that graph because I don't want to use like a third-party dependency to run it. I feel like I should be able to run such a simple neural network by myself. I should understand how to do that. And so like I'm trying to figure out if that is possible. So here he is saying that I am a multiply operation. And my inputs, I guess the inputs are my inputs are either, I could multiply two nodes together, but I don't think we ever do that. We only ever multiply an input by a constant because the constants are the weights that we've trained, right? Each of these edges has associated values. So we can probably say that like for each input, we might be like node ID 0, 1, and 2 are going to be multiplied by values like 1.1, 2.2, 3.3 or something, right? Like these are, we'll store our weights for this node that are its inputs. And we'll just say this is a multiply add actually, right? So we multiply each of these things by the weight here, and then we add them all up to get here. That seems reasonable. Sure. Sure, yeah, that seems fine. So then maybe our nodes, they might be, operation might be strong here. We might have to say like type. And then we might say that our like type can also be input. Sure. Yeah. Sure. That seems maybe reasonable. And then how would we store this? Okay, let's try like converting our first linear layer to this format and see if that makes any form of sense. So we have like net linear 1 weights. And I'm pretty sure we already looked at this, but let's just look at it again. Cargo, no, not cargo. I'm so in Rust land because I was programming in Rust yesterday. So he is 15 by 54, which makes sense. There are 54 pixel inputs. And so let's like just look at one of these input nodes. So net linear 1 weight 0 dot shape. This should just be 54. We have 1 for each pixel. Yep, cool. So I guess first we have to make all of our input nodes. Okay, that makes sense. So we can say nodes is equal to this. And for anything in net linear 1 shape 2. Shape 1. Yes. So here, oh wait, sorry. So here we know that this should be how many inputs we have to each of the nodes in our linear layer. We can say we will put a node. What's the like? Is it append in this language? Yeah. And we will append an input here. So I'll say type input. And I think that's it. That's all we actually have to think about here. There's no values to store here. There's no like inputs to an operation. It's just like, hey, somebody has to give us a value here. Okay. Yep, makes sense. And so here at the end of this, we should have a 54 length array that just has like type input over and over again. So let's print that out and make sure that that is what we expect. Unmatched. Maybe. Fuck you. Int object is not editable, right? Because it needs to be a range in this language. Okay, so 54 things in there, and they should all be just a dictionary that says type input. Perfect. Okay. So now we have our inputs, and we have their IDs. Their IDs are just going to be 0 to 53. And so now we can iterate over the weights. For weight in net linear 1 weight 0. We should be able to append. I guess maybe we want to take we want to enumerate this stuff too. Yup. And he's going to be now of type. He's going to append something to the graph that is type mul add, and his inputs are just going to be, I guess in this case, it's 0 to 54. So I guess it's just range 54 and convert that into a list. Yep. Yep. And values are going to be the weights. So we actually don't even have to loop here. We can just say that the values are net.linear1 weight 0 to list. Okay. That seems right to me. Okay. So here now we have a type. Our last thing is a multiply add with all of these inputs. And here are what we're multiplying by. And then we have to add at the end. So what if we want to like run this graph now? We would. Let's see. I guess we need to like flag our outputs in some way as well. And I guess like the outputs have to have like a defined order. Probably. I guess maybe instead of storing one input per node, maybe we kind of store them as an array. Aren't loops terrible for performance compared to list comprehension in Python? So the loops in Python are absolute shit, yeah, because you have to run your interpreter, and your interpreter has this like really slow lock and stuff like that. But I'm not really worried about performance here right now. I'm just trying to like nail down the data type, especially because like the end goal is to like import this loop in Rust. I just want to make sure that I have something that like works at all. So I've decided that we're going to store a number of elements along with our input. So instead of having one input per pixel, we're going to have one input that is all the pixels. Okay. Which I think makes sense. So now we should just have two nodes. One, which is the input, and then one that instead of taking in all of these inputs, he just says that his inputs are index 0. Which I think makes sense. The input is this node. So let's see what that looks like. So now we have input, number of elements, 54. And then we have a multiply add with these values that have 54 things. Okay. And then we can have an output. And the input is just the thing at 1. Cool. So now we want to like execute this graph in some way. And let's think. What does that look like? We basically have to convert this back into PyTorch. So, which probably involves walking the graph in some way and doing a PyTorch operation for each thing. For now, we know that we only have one input and one output. We can kind of like leverage part of the like information we have about the graph to do this. So we can say like what? For node. Okay. Let's say def serialize network. And we take in the network. And we basically do this. What we did here. Makes sense so far. We return nodes. So now we have like serialize network is equal to serialize network net. And then we want to find some way to run the network. Okay. So What does that mean? We haven't really thought about this at all. Serialized network. Let's think. So we can have our, like, we can store the node outputs in an array. Okay. And then we can say that we are looking for the output type. Sure. Okay, so we can say, like, output index in this, like, serialized network is going to be serialized network. Can you do, like, find in this language? Find. I want to find the index with type output. Python find index in list. It's been a while. It's been a while. How do I find the index? You enumerate and you just... Are you kidding me? Is that really? Okay, no, this is what I was looking for. Index returns the first. So the index of the value. Oh my god. Is there really? This can't be right. Python find iterator. Find the item from an iterable that matches a condition. Next x for x in iterable. That's probably what I was looking for. So I guess this is kind of what they were saying. So you do something like next x for x in serialized enumerate serialized network if x1 type is equal to output. Oh, you're saying no, just do list.index. Python list index. But do I have like a custom filter that I can't I don't know like the value that I want. I have like a custom function that I want to run to find that, and it doesn't look like it supports that. Let's see. So we have like dot index value start stop. Yeah, it's not like that clear because I have like a custom function that I need to run, right? So we can just do next x0 for x in enumerated serialized network. Sure, that should be good. So we can say print or output index is equal to this, and I guess we do like a none if this doesn't work, and then print output index. Okay, and then down here we can say run network serialized network. Hey, could you give me tips on how to learn Linux? My tip is just do it. Like, I don't. I think learning by like fire. What is it? Trial by fire is effective. So I think that if you're like, I want to use Linux, first of all, I don't really know what like learning Linux even means, right? Like, I know that like, I'm not saying that it's a bad question. I'm saying that like, it's such a broad topic, and like, what is like the goal? I think like you need a goal, right? What do you want to do? You want to like run Linux as your operating system, and you want to be able to like, or do you want to be able to like write software for Linux? You want to be able to like say that you can use Linux so that you can put it on your resume, right? There's all sorts of reasons that you could like, goals that you could have that like kind of shape what you're doing. So I think just like, if you have something that you're trying to accomplish, just try it, and you'll figure out pretty fucking quick what you don't know, and you'll just have to start Googling and trying stuff. I don't know. That's what I always do. But what do I know? Okay, there we go. So we should have like an output index here, and we should find that the index is 2. That's what we're hoping to see here. And we do see a 2 there, which is pretty sick. So we have found our output index, and we could probably assert only one output, but we don't really care about that for now because this is scratch code. Output. So we know our output, and then we just want to like work backwards from our output to find our input. So we can look at the input that we need. So we can say serialized network. Okay, first we're going to say that our node outputs is going to have none repeated for each element in the serialized network, because that's going to say, hey, we haven't computed anything yet. All of these values are empty, which seems reasonable. And I don't know how do you like just like repeat a value in a list in Python. Python repeat value in list. My list 1 2 3 4 5. How do I like my list append? I guess you just do it in a for loop. Is that what they're going to tell me? Python for beginners. That's so sad that I'm reading Python for beginners after working in Python for like 2 years professionally. God, that's sad. Yeah, okay. There's no like simple thing here. For I inland serialized network, node outputs is equal to this, and then we just say node outputs dot append none. So now we shouldn't ever have in rangeland every time. So now we have like for each thing in our computational graph, whatever you want to call it, there is a flag that says nothing's there, which means though that we can always index into that. And then we can say we're at our output. We want to work backwards from our output to basically fill the value that we need. So probably that's starting to look like some sort of class. Probably makes sense here. So we can call this like network outputs. Ugh, I don't like that name. Node outputs. Computational graph. Sure. And what's he having him? He's going to store the network ops. Okay. So this is a serialized network. And then we're going to also store output node outputs. Okay. This is starting to come together, I think. We're going to find out real fucking quick. So for I in range, then serialized outputs, self node outputs now. Okay. Then we're going to just say get value for an index in the graph. So we're going to look at self ops index, and we're going to look for his input. Okay. If he doesn't have the field input, we're going to figure something out. Not sure what yet. Oh no, that's fine. So we'll assume that everything has the type input, which this field does not, but we'll figure that out. I think I have a special case for that works. So we're gonna say for here, we're gonna look at the input, and we're gonna say input index is this. And if self node outputs IDX input index is none, we get the value of that thing and we store it. Self node outputs input IDX is equal to self.get value of input IDX. So now we have like this like recursive function that will like resolve all inputs automatically, hopefully. And then we just have to say, well, what does that entail? What does that entail? So I guess we also have to check if we've cached our current values. So you say self.if self.node outputs IDX is not none, we return it. We just return self node outputs IDX. Okay. Otherwise we have to compute it. So first we need the input. And I guess we don't have to do this. We can just say self.get value input IDX. And now the caching is handled automatically, so we don't have to worry about that. Input val is equal to this. Okay. And now we just have to say, what is my operation? So okay, well, first we're going to say op is equal to self ops IDX, so that we can work with that in shorthand and not have to do the lookup every time. And so then we just say if op is equal to multiply add, then what do we have to do? We have to multiply the input by our values. So input, I guess we're going to assume for now that our input is stored, we're storing our outputs as torch tensors. Okay, so input val, and we just have to multiply this by our values. So we can say op values, and we need to convert this into a torch tensor. Yes, this is probably going to work. So we just do input val times torch tensor, and then we sum them. And then we store that. Yeah, that seems right. And then else, what? We just say raise runtime error unsupported operation. And then we probably have to handle like elif op is equal to output. This is not op. This should be op type. Yes, yes, yes. So if we're on the output, then our self node outputs IDX is equal to input val. And I think that's pretty fucking close. We need to import torch. And we just need to special case input now. So all we have to do is pass in our input here. And we just find the item where the type is input. So we say for, let's see. We have to think. We have to think a little bit. Just a little bit. I hate thinking. So we find the item in our graph where the type's input, which is this like next x for x in serialized network if x type equals input. Otherwise none. We say input IDX is this, and then we want the index, so we say x0, and we enumerate this. Yes. Yes. Okay. And then we can look at the input index, and we just stick the input in there. So self node outputs input IDX is equal to input. And we probably have to turn this into a torch tensor. And we should probably do a quick check to make sure that the input is the right size. So we say the input operation is serialized network input IDX. And we can just do a reshape this into input op nom elements. And hopefully that should line up. So we should pass it, we can pass in then something that's like 6x9, a 6x9 tensor, and that will turn it into a 54 tensor. And that should just work. It's warning me about something. Argument of type int none cannot be assigned. Oh, because this could be none. So if input IDX is none. Raise runtime error. Graph has no input. Okay. Cool. Cool. I think that actually might work, weirdly enough. So now to run our network, we just create our computational graph. And we pass in the serialized network. And for now, we're just going to do torch.rand for 54 things, because I don't really care. I just want to make sure that like the thing will work. So torch rand, I think, will give me something of 54 elements. Probably have to specify dtype is equal to torch float 32, probably. And then we'll say graph get value 2, because we know that's the output. And let's just see if that like doesn't fucking crash. Okay. So, he doesn't like that this was none. So how is he none? Oh, because we just never return anything. Cool. So now when I run it, we do get a number, which is a very, very, very good sign. And so what can we do here? We could create a network with known inputs and check. Oh, well, we can look at get value 1, which is the output of our multiply add, which isn't really helpful. Okay, yeah, let's put in known inputs and known outputs, and then we can check that it's right. So we can feed in, let's feed in only ones. Okay. 54 ones. And our serialized network, instead of trying to serialize our network for real, we can generate like a mock network. It's the same, we will keep the same shape, except for the values here. We will just do range 0, 54. Is that right? Yeah. And so what we should get, if we did this right, is we should get 1 times 0 plus 1 times 1 plus 1 times 2 all the way up to 54. Yes. Yes, yes, yes. And we'll call this generate mock network. Okay. So here we gen mock network. And he shouldn't need to take this guy in, so here we're just going to hard code 54 here. And let's run it. Let's run it and see what we get. So 1431, it's a whole number, which is a good sign. And we can just say, what is that what we expected? So we can say for I in range 0, 54, sum plus equals I, sum equals 0, and we can print the sum. Okay, that's a really, really good sign. So I think that we just fucking first tried it, which is pretty sick. And we now have like this like graph that will automatically resolve its inputs. And so we should be able to just start feeding in extra multiply adds. Yeah. Let's do that. Let's do that. I think this is like a good checkpoint for a chapter in the YouTube VODs. So let's say figure out how to represent rates. We'll call this like generate single node compute node graph executor. Okay. And then we can say that it is 4840, and we are working on now extend graph to support more than one node. So I think all we have to do here, I think, is when we serialize our network, serialize network with the network, let's see. What are we going to do? So we have our weights. I guess we also have to add, we have to put in the bias as well. So nodes.append. We're going to say the type here is an add. Its input is 1. It's the output of the multiply add. And the values are just net linear 1 weight. No, linear 1 bias 0 to list. I think. And this should just be one number, I think. We should check that. So we will print out our network. Print serialized network. Network. And let's just see what we get. Unsupported operations, so that makes sense. But our serialized network should have a type add, input 1, and his values are just one number. Perfect. Perfect, perfect, perfect. So somewhere here we have mul add, and we just add another operation add. And we just say the output is the input val plus the values. Sure. That makes sense to me. So now, does that run? Unsupported operation. We should probably log what the operation is. So we can say op type is equal to op type. And we really should be doing this up here anyways, because it's stupid to like index, like do a hash lookup every time. So on each of these if branches. This guy's name in chat is fire in the hole, and all he's typed in chat is fire in the hole in all caps. Oh no, he's chopped other stuff here, but that's funny to just see him like yell his catchphrase. Okay. And so we can log the op type here, like this, with a little f string. Boom. So what's it bitching about? He doesn't like that mul add is an unsupported operation. Hello? Oh, it's because I didn't write elif here. Okay, so that ran, which is good. And we know that the value is minus 694. So if we just don't run that part, we remove that from the graph, we should see the value increment by 694. 0.694, which it does. 29.0 to 29.7. Solid. Okay, so it looks like that's probably working as well. So we now have our multiply add and our add, and now we just have to do this for every single node in our linear layer. Okay. That seems right to me. So we can go for I in net linear 1 weight. Yep, that makes sense. We are going to multiply add the weight to list. And so this should be called a weight. Then, for each of those things, we're also going to do an addition, right? And those are going to be the bias. So we can maybe do weight bias in linear 1 weight. How do I want to handle this? First of all, I'm forgetting the shapes again. It's hard to keep track of all of the dimensions in here. So we can say print net.linear 1 weight shape. And let's just print the linear 1 bias shape as well, just because I'm lost. I'm fucking lost, as always. So our weight is 15 by 54 and our bias is 15. Okay, yeah. So we can actually do we can do this. We can say for I in range weight shape 0. For each node, basically, of the first linear layer. We are going to do a multiply add that takes all of the inputs. So we're going to say weight is equal to net linear 1 weight I, and the bias is equal to net linear 1 bias I. We're going to do a multiply add, and then we're going to do an add on top of that, so the with the bias. Bias to list. And I think that's it. I think that's it. So now what we can do is we can run this and we can compare what happens if we just run the linear 1 layer as it was in PyTorch versus as we do when we try to reconstruct it from this graph. And we can see if the outputs are the same. So first of all, that does run successfully, which is a good sign. Except our output here now needs to be something else. So our output right now is like a single number or a single node in this graph. And now we want it to be something else. What's also kind of odd here is our input is like a single element, and our multiply add takes in that single element. But if we were to stack multiply adds, then that would not be effective. So we might need to think about that. We'll cover that. We'll handle that when we get there. For now, though, we will say that our output let's like maybe sum up all of these, which means that our output needs, like, we need an operation for summing nodes. So we can say what nodes.append sum. So we have an operation. He has type sum. Inputs. Input is going to be, now he's going to be like an array of nodes. And that seems fair. And now we just have to track which nodes we want to sub. So first of all, these inputs are wrong, actually. This input should be, input is 0, that's fine. But the input for the add should be the nodes len minus 1. Len nodes minus 1. Because we're trying to add to this multiply add. So this multiply add gets inserted, and then we say we're going to add like a constant offset to that thing afterwards. Great. Great, 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 great. Okay. Then this sum now needs to take all of the outputs of these adds. So maybe we can say add outputs is equal to this. And then we just say add outputs dot append nodes dot len nodes minus 1. Okay, which means that the input to the sum can be the add outputs. So what we should do here is we should take all of the linear 1 weights, multiply them by the inputs, then add their biases, and then sum the output. And so if we then do, when we run the network, and then maybe we take in the original network as well, we can say net linear 1 on the input. So we can say input is equal to torch 1's this, right? Just once. And we can run net linear 1 on the input and then sum that. And we can say original network got this value. And then we run the graph. And now instead we have to get the value of, let's add a function on here that's like get output, because that's easier. And all he's going to do is he's going to find the output index. So similar to this input index thing, except he's going to look for output. Self ops, and this is going to say output idx, and he's going to return self dot get value of output idx, which means that over here we should be able to say graph get output, and we should be able to say reconstructed got this. And hopefully those two things are close together. We have to pass in the network here. Reconstructed got this. Original network got this. So these are totally fucking different. Which is not a good sign. Not a good sign at all. Let's make sure that we are passing the exact same input in to both of these. Yeah, not good at all. We're saying original network got 580, reconstructed got 29. So Why is that? Let's look at, say we like take our linear 1 on the input without summing. Let's see what that prints out. Original network got 1, 2, fuck, why am I counting when you can just type shape? So the output here should be 15 values. And they are 15 values with like, the first node has an output of 29.03. Let's run our graph and just run it on the first node. So what we should be able to do is we should be able to look at the first output of the add, and we should see the same thing. So this should, we can call get output of a 0, 1, 2, and see what that gets us. So if we call graph get value of index 2, do we see a 29.035 in here? Which we do. 035. We do, which is a really good sign. And if we say get value 4, which should be the next one, do we see the 8.54? Okay, that's a very, very, very good sign. Very good sign. Because that means that we're like basically there. So what the fuck? Aha! I found it. So here, we are looking at the output of node 1, but this should be the output of basically nodes, len nodes minus 1. Okay, and now when we run this, hopefully it'll say, it should say when we try to get the output that we haven't implemented the sum type yet, which is what I should have expected from the start, and I forgot that I should have expected that, so. Where am I looking for this? It's here, graph, get output. Okay, so what's he complaining about? 1, list indices must be integers or slices, not list. Ah, okay, so here our sum is, his input is like multiple things, not one thing. And so we actually have to detect that. So somewhere we have, here is our input index. And I guess here we can say if is instance IDX list, I think. If the index is a list, is that the right way to do this? Yep. Then we just say output is this. And for I in index output dot append self get value I. Nice. And then we return output. That seems right. That seems right. So we check if like we're trying to get the value of a list, and if it's a list, then we just like get the value of every item inside. Easy. Okay, so now we're on unsupported operation sum, and we just can, that should be easy to do. So if the type is sum, then the output is torch.sum input val. Easy. Fucking easy. Fuck. We need to convert that to a tensor. Reconstructed tensor got 580. Original, I think, also got 580. If we go back to here and we say sum. Hell yeah, baby. Okay, dude, that's so sick. That's so sick. So we're at the point now where we've reconstructed our first linear layer. That's so sick. Okay, now we have to stitch that together with the second linear layer. So let's maybe say that's another good checkpoint in the VOD. And now we want to link multiple layers together. So let's temporarily pretend that there's no rel u. In that case, we have all the operations we need, And we just have to make sure that like once we get the outputs of one layer, we can then shove them into the next. So what does that look like? It's going to look very similar to this probably. We're going to iterate all of our weights and biases again, except this time for layer 2. Okay. And the inputs are still going to be multiply adds, except they're going to come from somewhere else. It's probably going to be add outputs I think. Let's think this through. So this guy is going to have 15 inputs. The I is going to go from 0 to 15. This guy had 15 outputs. So it makes sense that we just take the output from the last thing and we stick it as our input to this thing. Except that's not true. Our input is not an individual node, but it's actually the collection of nodes. So the 15 outputs that we got here are going to be the 15 inputs to this. Okay. Which kind of is like different than here. So I think we're back to the problem where we actually shouldn't be structuring our input this way as like a single thing with number of elements. I think we should go back to putting this as for I in this. For I in range this. Nodes.append this. Just an input like this. And then we have to fix our execution of this thing. So basically, our multiply add now should be taking in lists of numbers. So list range 54. Nope, this should be range net.linear1.weight.shape 1. Okay. And certainly somebody's not going to like that. So here our input should be a list of the right size now. And our input indexes are now lots of them. So how do we do this? We have input is going to be an array of 54 elements. And our serialized network is going to have 54 inputs. So if we say x for x in... Yeah, okay. I think I got it. So instead of just doing next here and getting the first thing, we're going to say, give me a list of all of these things. Yeah, give me a list of all input indexes. Input IDXs. And we should see a list of 0 to 54 here. Okay. And we should see print input should be 54 different elements. And I think if we just run this, we're going to crash after that, but perfect. So we see indexes 0 to 53, perfect, and then a bunch of ones of the same shape. That's perfect. Perfect. So we can say input assert input indexes length, yes, is equal to input shape 0 because it's a tensor. Okay. What do I want to do here? I'm just like sitting here stuttering like a fucking dumbass. We just want to put each thing in. So input. I guess we like can zip these two things together. For I in len input IDX is perfect. Like this. That makes sense. We can just say input self node outputs input IDX is I is equal to input I. Yeah. Okay. I think that makes sense. I think, maybe. And then for our multiply add, our input value is going to be, I think this might just work. And we might have to write torch tensor here. But I think otherwise that'll just work. Look at that, baby. I love it when shit comes together. So our original network and our reconstructed network are still getting the same values. And now we should be able to tack on a second layer here. And I think it'll just work. So now we're going to run linear 1. So we're going to say net linear 1 on the input. And then we're going to run net linear 2 on the output. And then we're going to sum that. And we should get the same value as our reconstructed graph. So we can say original network got out to sum. And let's see. Original network got this thing. The reconstructed got this other thing. The reconstructed network actually didn't change anything, which is kind of weird because the sum is summing the first layer, not the second layer. We didn't check this, so we should say, maybe we should call this, instead of add outputs, we'll call this out1. Okay, and then we'll say out2 is equal to this. And then we do the same thing where we just say out2.append these indexes, and then we run the sum on out2. Now when we run this, do we get the same fucking thing? Let's fucking go, baby! Oh, it just works. Oh, it's so sick. That's so sick. Okay, so now the only piece we're missing is the rel-u. So in our network, between these two linear layer runs, we just do a rel-u in between. So we should probably just on all of these guys, just type rel-u. I guess we should probably do the rel-u as one operation. So we can say out 2. First let's rename out 2 to out 3. Because this is the third operation now. And now out 2 is just going to be the output of a rel-u for all of these guys. I think that makes sense. So for I in length of out1, in the range len out1. Oh, I guess, you know what, this is wrong. Fuck this. I'm just gonna tack it on after the, Hold on. I don't want to lose this. Okay. I'm just gonna tack it on here. So for each thing here, after our add, we're just gonna fucking shove on the rel-u. And the input is this thing. The previous node that we inserted. And the value, there's no value for a rel-u. And I think that's it. Okay. So if our op is rel-u, we just do this. Torch rel-u and torch input. I guess here our input is always going to be one thing. So we can just say input val here. Okay. And now, maybe, is that really fucking it? If I then run a network on the input, I say output is equal to net input. And we'll do the same like little sum shit. We'll make sure that our sum is on the right guy. He's still on output 2, but there's just this linear rel-u in the middle. Hell yeah, baby. Oh, that's so sick. That's so fucking sick. Okay, now I think that's it. I think we've got like a format now that can run the graph. Okay. Now what? We have our output as a single value, and I guess that's not quite true. Our network outputs one number for every single character. So I guess what makes sense here? Defining like a bunch of inputs and a bunch of outputs, it seems maybe a little silly. I'm not really quite sure that I like this part of the thing. It feels like we should be able to say that no, fuck it. We're just going to have every node in our graph represents one value. That makes it very simple. And so our output, if we want to have multiple outputs, we just have to put the multiple outputs. And maybe we can say that if the order of the outputs is important, they just have to be inserted into the graph in the order that you want to look at them in. I think that's fair. So instead of summing here, we are going to say for I in range len out 2, we are just going to say that these are outputs. And the input to our output is going to be out to I. And now we can get value of all of our output indexes. So we'll say that the output idx is equal to, we do the same thing we did for the input here. So instead of just getting the first one, we just convert this whole thing into a list. And we get the value of output indexes. And so then I think we can delete that sum. We already did. Perfect. And now if we run this, perfect. We get a list of tensors, which is great. And we can even now, instead of doing this output sum, we can do output original network got this thing, reconstructed got, and then we'll call graph get output, and then I think you like torch.cat to put them all into one thing. He doesn't like that. He does not like that at all. Which is odd to me. How do you like torch list of tensors to tensor? I thought it was cat, but maybe it's not. Yeah, torch.cat AB. So why doesn't he like that? Let output, not let, output is equal to graph get output and torch.cat output. Print len output. Like, am I high? Like, am I high? Zero-dimensional tensor at position 0 cannot be concatenated. Why? Print output. Oh, these are zero-dimensional tensors. So you're saying that he's saying that they can't concat. Maybe they want torch stack. He'd prefer maybe. Maybe. Yeah. Okay. There we go. Perfect. So let's stop printing garbage that we don't want. And let's see if those guys look. Oh, fuck, that's so sick. Woo! And then we can do, we can even check here. We can say print is same question mark. And we do what? Output minus input is less than some epsilon. And then we say, are all of these true? Are they all the same? He doesn't like my output. Oh, because this is output minus. fuck, this is net output, we'll call it. And we'll say output minus net output. Is same, question mark? False. Fuck. Let's say minus 1e3. Okay, so there's some error here. Probably from serialization and deserialization of the weights. But they're close. Close enough, right? What we should probably consider in the future, not right now because I don't want to right now, we will say somewhere. We want to consider storing binary representation of floats to avoid serialization, deserialization, numerical imprecision. Okay. But that's fucking sick. That's fucking sick. So here we can actually say it wasn't just linking multiple layers together. We can say this like running the full network in Python. And let's see, we're at 120, which I think is probably enough to like save this and load it. Try doing the same thing in Rust without Torch. Probably. So let's say maybe we go to our network file and we just say serialize self, and he just runs this essentially. Okay. And maybe here we probably don't want to lose this code, so we're going to also take this stuff and just shove it in here so we don't lose it. Because that would be a shame. Okay, get status, get diff, cool, get add -u, get commit -m, serialize network to intermediate into custom graph representation. Sick. Sick. Okay, so now we can come back to our test function, and in main now, we'll serialize the network and just save it. So import JSON, which is surely just dumping all of this as a JSON blob is probably wrong, but that's okay. Also, what I'm realizing is this numerical imprecision doesn't make sense because there's no stringizing of things going on here. This is just going to and from like Torch to Python and back, which is kind of fucked. But that's okay. That's okay. Okay. So then we can just JSON dump serialize network to a file. So dump takes the object on the file pointer, so we can say with open network graph.json as writable. Dump this into the file. Okay, and now if we run test.py, we can look at the network graph. First of all, let's see how fucking big this thing is. Oh, that's not that bad. Is that, what unit is that? du-h. 784,000. Okay, that is kind of bad. That's like a megabyte JSON. But that's okay. Oh shit, my editor. Oh god. Cute. There we go. Okay, so I guess we make a Rust mkdir application, I guess. And cargo new bin. Or can we say cargo init bin dot or something? We need cargo. So let's get our usual Rust friends. So we have Rust up, Rust analyzer. Probably that's it. Probably that's it. And we just need to give it a sec. Give him a second. There we go. And go back into our application, cargo init bin dot. We have added a binary application. We'll call this what, like, we'll just call it app. That's fine. Doesn't fucking matter. And we say cargo add surdy JSON. We need to make sure that it's surdy underscore JSON. Don't want to accidentally get some sort of like fucking typo squatter. That looks right. And if we go in here, we also want the derive feature here. So we say version is equal to this, feature is equal derive. Okay. Okay. Cargo check. Make sure. Nope, we fucked something up here. This guy wants an array, if I remember correctly. There we go. Which pulls in a bunch of extra dependencies, but that's okay. And now we can go, oh, look, edit, get, ignore, and ignore target. So that when I edit, when I open Telescope, it like knows, it looks at the get ignore and it goes like, oh, that's not good. I don't want that. So perfect. And now we can just try to load the file. So weights const network definition is equal to include bytes dot slash network graph.json. Okay. And this guy is just a bunch of U8s. All right. And then we can just say surdy JSON from slice network definition unwrap. And let network definition is maybe first we just do a surdy JSON value. We let him, without any like definition on our part, let's just see if we like, if it deserializes correctly. And we can say, what is this thing? Can we print it? Who knows? Cargo run? Nope. Cargo run. There we go. Okay, so it parsed successfully. And sweet. Okay, that's looking good. So now we need to like say, what the fuck is this thing? So we can say we have a bunch of nodes. So what do we call it in the Python side? We called it source. Hello, lib network. We said we had operations. Node op. And his options are mul add, mul add relu. Is that it? Mul add relu, mul add, oh, input output. Okay. And each of these guys has things that associate them, but they're all kind of the same. Not really. Some of them have options. Some of them have fields that we don't have. So we'll say what? Input. He has no values. Mul add has input, which is a usize. Values, which is a his input values, I guess, are always a vector of floats. The inputs are not usize, actually. They should be vec usize. Okay. Add, what does he take? Add has an input, which I think is always just a single value for us right now. So we don't have to handle the like fact that it could be multiple different things. And the values are one thing right now. I think, as well. And the rel u has only an input. And output also has an input, this. Okay. So we want to derive, serialize, deserialize, debug. We use serde, serialize, and deserialize. I guess technically we only need deserialize because we are only consumers of this thing, not generators of this thing. Okay. And now, I guess we need to make sure that we set the options that will make this map into what we expect here. So one is that everything needs to be turned into snake case. So let's see, serde snake case. Container attributes, serde rename all. Is it out with quotes? Rename all is equal to snake case. And then we found this field the other day, which was the way that we store enum representation. So, fuck. Variant attributes, maybe? I forgot where it is already. Field attributes, container attributes, enum, tag here. Yeah. So here we have serde. Tag is equal to type. And then somewhere there was, oh, here we go, enum representation. This is what we're looking for. And the values are just like the things that we expect to be associated with this thing are just next to the type. So we have adjacently tagged with content in C, which isn't what we want. We just want tag is equal type. And that looks very similar to what we want. Okay, so I think now if we say that we want a vector of node operations, I think that this will still work. Maybe. We'll find out. Cargo run, baby. Nope. Expected U size found floating point. Line 1, column 2432. Okay, let's improve the way that we can diagnose this. So if we go to our test pi, we can say dump with indent equals 2 so that we get like multi-line JSON. We can run this. And now when we look at our network graph, now this looks, it has lines that we can like at least look at. It has 72,000 lines, but at least we'll get like, hopefully, some better diagnostics here. So here's to say line 284. So we can look at network def graph 284. So we are looking at the rel u. Oh, maybe he's looking at, oh, what the fuck? Line 284, column 2. Rel u, input u size, add. Oh, values of float here. It was just a little off. Otherwise, oh god, that's so sick. Okay, so we have successfully parsed the graph into our bunch of node ops. And now we can just go back to our network pi and start like porting the same thing that we did here for our computation graph into here. So computational graph. And he's going to look very similar. He's going to have ops, which is a vector of node op. And he's going to have output cache, which is a vector of option of F32. Okay. Impl computational graph. And he is going to take in a new thing. And he's going to take in the network, which is the vec node op. And inputs, which are vec F32. Okay. Cool. Cool. Now, what are we going to do here? What are we going to do here? We're going to say, return a computational graph. And this is simple. it is computational graph with the ops is the network, and we are going to have to do the same shit that we did here, where we look for all inputs. So we say let input indexes is a vector of usize. Okay. And he's equal to inputs fine network fine iter enumerate. Okay, so we're gonna have the index of each thing in here, and we're gonna say filter for index item, and we're filtering for item. I guess we match the item. No, we just say if let node op input is equal to item, true, else false, and then we can then map this to the index. IDX item goes to IDX, and then we collect this. And this should give us our input indexes. Similar to this bullshit here. This bullshit turns into Rust bullshit, but they're both bullshit, you know? Okay, so then we can say for I in input indexes, for IDX in input indexes, we then just say, I guess we need input IDX, output IDX in what do I call this? For I in input IDXs.len. I think that makes more sense. In 0 to this, we can say inputs I go into we need an output cache. So we say let output cache is equal to vec none for network len. We have no outputs cached. Then this has to be mutable, and we say output cache input IDXs I equal to inputs I, just like we did in Python land. Okay, and then we can say output cache here. Try wrapping in sum. Okay, sum works for me. Bing, bang, boom. And we have our initial state. Now we just need to do the same, like get output or get val for self at index, which we're going to do the same thing that we did in Python land, certainly. And so what do we do here? First, we check if the input is a list. We don't have to do that anymore, I don't think, because we should know based off of the type system. But we'll see. Maybe not. We might have to actually make an enum for this list or value type. Okay, so first we can say if let sum val is equal to self output cache get IDX. No. IDX. Yes. Because this is a vector of options, so if the thing at that value is something, then we just return the thing. So this is just a float. Always a float. Otherwise, we actually have to calculate the thing. So what we did here was we checked if it required an input. So we can say let input IDX is equal to match. Well, first we have let op is equal to self ops at index. Okay. And we match on the op. And we have all of these guys. Womp womp. So then we do a little bit of formatting like this. Okay, and we delete types. Okay. then we say we have to do something. So panic here. Input has no input. Or I guess we should say input should have been resolved already. Here, we are doing the input is input. Okay, here the input is input. Rel U input is input. And output input is input. Okay, easy. Now, where this is probably going to get fucked is I think that these input types are different. I'm pretty sure some of these are, I think some of them are vectors and some of them are single values, which is going to be a problem. Certainly a problem, yep. So the multiply add inputs require many inputs, and the add requires, all of these are only single input. Now, we could force these into a vector no matter what, or we could just say enum input is equal to, we have either single usize or multi, and it's a vec usize. Easy. Okay, this, we won't put this as part of the definition of the thing because that'll fuck up the JSON parsing. So here we'll just say input multi, and the rest of these we say input single. Okay. All right. And maybe we shove this into a function. Function get input for op. Or maybe we even put this as a member here. Wow, that's fancy. Fancy, fancy, fancy. Function input self. He returns an input. And we just yoink this shit, shove it in here. He's actually at the right indent level already. Surprising. Here we match self instead. And we should be good. Implicit returns thing. Because we put let here. Okay. Try using a conversion method to vec. Let's see. Do we... Yeah, fuck it. We'll just clone for now. You could maybe get away with using these as references, but I don't want to. These guys need to have ignored fields as well, I think, like this. Yeah, like this. Boom, boom, boom. All right. All right, and then here we say let input is equal to op.input. Wow, fancy. Look at that. Look at that. Okay, which probably means that our get val probably needs to handle that, but we'll see. We'll kind of see where it evolves. So what did we do after that? We matched on the type. Okay, and just depending on what the type was, execute it. So we can say maybe function execute self, and he takes in an input, which is of type input. Okay. Yeah, I think that's right. Well, this is like input indexes, and we might want like input values as well. Because if we're executing, we need the actual floats that we're running on. So maybe what we'll do here is we'll rename this to input IDX, make sure that still compiles, which it doesn't, so 84 GG unimplemented. We are at 90. We need to borrow here. Okay. Otherwise, things compile. Great. So now we can have enum input, and this is going to have the same things, except instead of it being indexes, he's just going to have values. Which means that here we can make a execute function. and he can take in the input, probably as a reference, and he's going to output an input. Is he just going to output a float 32 no matter what? I think he is. With the way it's currently laid out. So then we do the same shit, match self, do something depending on what we get. And then values, we need to like actually use these things. So panic cannot execute an input. Okay. And then these guys all have something. So output, here instead we're going to say values, or output takes input, and we actually don't care about anything here. We know that the output only takes in the input. Okay. So here we say input. And I think that's it. I guess we have to match this thing. So we say if let input, we say match input in here. And if there's an input single, we're fucking golden. If it's a multi, there's multiple things here, that's unexpected. And we can say panic unexpected multi input for output node. Boom. For ReLU, we are going to look at, we don't give a fuck about any of the things in here for ReLU. And for add, we only care about values, and for mul add, we only care about values. Perfect. Okay, so for mul add, we're gonna say let input is equal to match input, and we're gonna do the same thing here, except we're gonna swap them. So multi gets forwarded on, single says unexpected single input for mul add node. Okay. Then we say if input.len is not equal to values.len. This is again a panic unexpected differing lengths of input and values for mul add. Perfect. Otherwise, we just say for I in 0 to input len, output is a F32 0. He starts at 0. Is that true? No, it's not. Maybe it is. We say input I times values I. Oh yeah, output plus equals this. Cool. And then we return output. Easy. Easy, easy, easy. Okay, so for add, why is add called values? He's only a single thing. But I guess, can we do something like, fuck it, we'll leave him as values for now, that's fine. That's fine. So we do the same thing here. We check that he is a single, so we'll say let input is equal to input, match single, unexpected multi-input for add node. Okay. Okay, and then we just say input plus values. Easy. ReLU should just be the same thing. We expect one thing, and we just say max 0 input. I'm pretty sure that's what the rectified linear function. Pretty sure. Okay. And output, we just copy the input, so that's done. Done. All right. Wow. I love it when it just works. And so now we say op.execute input, but we can't do that because this is the input indexes. And we just say match input indexes. And if, let's see. So if we have input IDX multi, we have to construct a vector of inputs. So inputs is equal to vec new. And for IDX in IDXs, we just say inputs.push self.get val IDX. Okay. And if we are, then we return inputs, input multi inputs. Okay. And if we have input IDX single value, it's just the same thing, but with only one. So we say get the value at IDX and return that as input single. Okay. So now we can say let inputs is equal to this, and we can just run the op. We say op.execute inputs. And then we store that in our cache. So we say self.output cache IDX is equal to this. With sum. Okay. Which he doesn't like, actually, for some reason. Consider borrowing. Ah, okay, sure. And then we just return that. So return, I guess we cache the result. Let res equal to this, and then we cache the res and return the res. Boom. He doesn't like this, like, fucking double borrow shit. That's fucking annoying. And unfortunately, the only thing we can do there is we have to split this out into a external function that takes in the cache separately. Ugh. So we can call this... Ugh, that's fucking annoying. So... Oh, we can't even really do that. Okay, for now, fuck it. We dodge the borrowing problems by copying data, even though we know we don't have to. Okay. Maybe that's fine now. Okay, cool. Cool. And then we had that get output. Which returns a input, I guess. So we're gonna have to rename this. Fix me bad name, because output can be an input. Rolling eyes emoji. And what do we do in the Python version? All we did here was we found we iterated and found things that are output indexes. So, boom. Except we need to say we are doing the same thing, but for output. Okay. We need to take in self here by immutable reference, or immutable reference, sorry. And then we just say let outputs is equal to vec new. Sorry, no, outputs is just going to turn a vec of F32, I guess. Yeah, that works for me. Then we don't need to worry about that. And we say, for IDX in output IDXs, outputs.push self.get val IDX. Then we return outputs. Cannot borrow self as mutable, because, you know, so we're at mute here. And I think we're chilling. So now we should be able to say, let graph is equal to computational graph new, based off of the network definition. And I think what we're going to do here is I want to just have the same values we were testing with here. So we can say we were doing 54 ones. So I think we can just say 1.0 F32 54 times. We have to say that this is a vector. Okay. Network definition. And then we should just be able to say, what the fuck is it bitching about? Oh, because I can't print after. Okay. Let me just say graph get outputs. Print line. Okay. And part of run. Moment of truth, baby. So we have 706, 1696, 449, all negative. Do we have our fucking outputs from before? I guess we go back into our test Python. And run net dot fuck. We lost the code kind of. So we're gonna go back to network py, take all this commented out code, copy paste it back over here because I don't want to deal with imports, and run the network. Run network. Serialized network. I think we took a net here as well. Okay. Python 3 test.py. Let's see if we got similar values. 706, 1696, 449. 706, 1696, 449. Let's go, baby! Let's fucking go! Alright. So, I think we got what we wanted to do. We loaded our network, executed in Rust. We got the same outputs. This ends at -808, -808, 554. It's like close. 17, 164. Pretty damn close. So that's pretty sick. That's pretty sick. And so now we're at the point where we can like start building on top of this and actually like running it for something. It'd be cool to see if we can do like how fucking fast is this actually? I'm kind of curious. So if we go to our main, can we just like I guess we can just time this. No, I don't want to time the whole thing because I don't want to time loading. So let's say let start is equal to stud time instant now. End is here. And print line. Why did I copy paste that? Print line took this many seconds. And we can do end minus start to sex F32, I think it is. I can't remember. Oopsies. Cargo run. Could not find. CD that. Cargo run. He doesn't like that as sex, not to. Of course. Of course. Wow. Oh, that's 0.1 milliseconds, but for a single sample, which isn't really a fair comparison because we're gonna have to check for like a 1080p image. But we could. Whatever. That's pretty fast. It'd be interesting to see. Well, okay, we can check this real quick. So our samples are 6x9. Our original benchmarks were at 12 sample size of 12. So we can just calculate how many 6x9 samples fit into a 1080p image, then quarter it because that's how many it would be at 12 pixels. And okay, yeah. So we have 6 pixels. It's 1080p. 1080 over 6 is 180. 1080 over 180 out of 10. Fuck. 180 out of 1080 is that times 1920. So you have 320 by 180. And then we quarter that for however many. So 14,000. So 14,000 times 0.000130968. So we're at like 2 seconds to run the neural network on our GPU or in our Rust code as it is right now, which is slow as fuck compared to the like 10 milliseconds that we saw when running with PyTorch. So I think what would be fun is to look at like SIMD and seeing if there's a way to like optimize this with SIMD, or maybe just optimize this in general. We might be doing a lot of like stupid shit, right? We've got to like batch commands. Rust 1 is on the CPU. Rust 1 is like not only just on the CPU, but it's like in the dumbest way possible, right? We just like construct our graph and just like did like the first thing that we thought of to try to like run it. So it might be fun to see how much we can optimize that, because it's like so much fucking slower with the way we've architected it here. But I mean, this is like a launching point, which is pretty fucking sick. And probably there's some sort of graph optimization techniques we can apply to make this go faster. So you're porting this project for Python Rust or just inferencing in Rust? I do just want to infer. I just want to run inference in Rust, and I didn't want to tank like the PyTorch or Onyx dependencies. I wanted to see how far we can get it on our own. At the very least, we understand it, which is good. Like, doing this exercise proves that we know what the network is doing, but it does not prove that we know how to do it fast. So that's probably what we'll do next. We'll see. I might have to do some reading, and we'll see tomorrow if the reading that I do ends up being like effective enough for me to do a stream on it. But yeah, I think that's what we're gonna do next is try to like speed it up. Or if I don't get there, then we'll probably work on maybe trying to integrate this in some sort of application of some form, like either like a web app to click the button and like upload an image and get a thing out of it in WASM, or maybe like something that pulls FFmpeg for my my video camera and tries to like replace my little camera in the bottom right with like an ASCII version and see how much that sucks or doesn't suck. So that's what's coming up next. If you like what you saw, I stream most days around 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you miss a stream, there is a YouTube link in the Twitch description, and all the VODs will go up there. There's a GitHub link there too, where project code should eventually end up. And a Discord if you want to chat about stuff while we're offline. I also post like announcements when VODs go up and when stream is coming up with a little bit of notice. If you're watching on YouTube and you want to pop by and say hi, there's a Twitch link in the YouTube description. Other than that, I think that's it. Thanks for watching. Have a good one. Catch you in the next one. Bye.